is 11, but I only see 3 participants, so I guess the team call is still going. I will give it a little bit longer so we get more people.
Ian, I think it's safe to say that team call ended and that we can start.
Okay, sounds good. Thanks everybody for joining. My name is Ian Baum. I am on the build team here at GitLab. I will be talking today on the highly available PostgreSQL option that we built into Omnibus that we're working on getting released for general availability in the upcoming release. So I guess let's move on. The first step is what is high availability? The main thing is that high availability is just, uptime. We don't want outages to a crash database. We don't want to the users to notice that there's something wrong. So if we have an issue on one node, we want to be able to move over seamlessly, have the application be available as much as possible. HA isn't load balancing. We're not, the goal of this isn't to kind of spread the load out among a bunch of servers to kind of make everything a little bit more efficient. It is merely just, uptime, keeping things available. It is not disaster recovery as well. So that's something like, if you're looking for geographic separation, that is outside of the scope of what we're looking for. So the main thing we were aiming for in building this is we wanted HA to be easy to set up. Normally HA is not easy to set up, and that's not necessarily a good story for users. So we want to make it as simple as possible. Somebody can follow an easy document and have a highly available database ready to go to back their GitLab instance. We want it to be fully integrated with the existing Omnibus workflow. You shouldn't have to go outside of Omnibus or GitLab in order to get this up and running. You shouldn't have to install a third-party package. You shouldn't have to make any changes to your infrastructure. It should all work within the normal workflow of administering GitLab. We also wanted it to be useful for GitLab.com. They need an HA solution just as much as our users do, and so as part of our normal dogfooding procedure, we wanted to make sure that this was something that they could take advantage of, and then we can tell our customers that, hey, we use it too. This is something that we find useful. So in order to do this, we kind of had to get a bunch of different products all built together and talking to each other. So the first one is Postgres. This is the database itself. This is where we store information on merge requests, issues, users, information like that. The next component is rep MGR, it's called. This is something that's used, it makes it easier to spin up a cluster of Postgres nodes. So they do the initial sync of data, make sure they know who the masters is. It also offers sort of some monitoring situation and can handle the actual failover process from one master to another. The third component is console. This is a service discovery and key value store. Someone's unmuted. Thank you. So console is used to kind of all the different nodes kind of tell console what's going on, and other nodes will then ask console for information. So this is sort of what kind of, it facilitates basically the communication between all the different nodes in the cluster. And the last component is PG Bouncer. This is a Postgres connection pooler. It kind of handles, kind of consolidating connections between an application and the database. It's kind of serves a dual purpose right now on GitLab. We'll get more into that later. But right now, it's sort of the middleman between the application and the database, and kind of controls where traffic is sent to and things like that. So first I'll talk more in depth about what we do with Postgres. So we set it up, the cluster's running up in an active passive setup. So that means we have one node is the master, and this is the only node that can accept writes. So if you want to update a row, insert a row, delete a row, it has to go through the master. The standbys can accept reads, and there is some support built into GitLab to have that traffic, read traffic routed to the standby nodes. We won't be really getting into that there, but it is a possibility. The second note is we use the write-ahead logs to ship all the changes from the master nodes to the standby. So that as writes are happening to the master nodes, they're sent to these logs, and these logs are then shipped to the standbys, and then the standbys apply these writes to their copy of the database. This is asynchronous, and it does have some possibility if the master node crashes in the middle of a write and the logs have not necessarily been shipped to the standbys yet, there is a small possibility of some data loss. We use streaming replication to ship these more frequently, so that minimizes the exposure a little bit. Normally the default behavior for write-ahead logs is it writes up to a certain point, and once it reaches a certain size, it ships that log off to the standby servers, and that does give you a bit of a gap. So the streaming replication ships more frequently, ships as it happens, and we have a smaller window of time where we might lose data. And finally, GitLab.com does use replication slots. Rep Manager can manage those for us. It does support it, and you can turn it on. We aren't recommending that by default, but it can be done, and it might be something we consider. We change our mind on it in the future. But replication slots kind of keep track of where the different allows the master to kind of keep track of where the standbys are in getting everything. So it's kind of, you lose the chance if a standby goes away for a little bit, the write-ahead logs might get deleted before it comes back. But with replication slots, it gives you a little bit more freedom, so you won't necessarily get too far out of sync and then have to reinitialize a standby server. The next tool is RepMGR. It automates the process. Normally for setting up a standby node, you kind of have to do initial sync of the data, then you have to set up the recovery.conf, tell it who the master is, who you need to talk to, how to connect to it, and then keep that up to date. RepMGR does all that for you. You just initially run it 2 commands. Through GitLab control, we've got it actually down to 1 command. You just tell it to set up a standby. This is the master node. It will contact the master, pull down the data, and then tell the node that to keep following that node. It also does automated failover. It's got a daemon built into it, repmgrd. Appropriately enough, it monitors the master node, and if it notices the standbys can't reach the master, it holds an election basically to say, master's gone, who's going to be the new master, and then it kind of facilitates that. And once they decide, it'll then promote the new node to master and tell the remaining standby nodes now follow the new master node. PG Bouncer, initially PG Bouncer was brought in, Uric brought it in to kind of facilitate, to lighten the database traffic by pooling all the connections together. It's a lot more efficient. You don't need to kind of set up and tear down connections as quickly. So that was initially brought into that. He did just, I think yesterday or the day before, we posted a blog post that he wrote about how he used PG Bouncer to kind of scale the database. There's a link there. There's a link at the end of the presentation if you want to read more on that. It is a good read, so I recommend it. But a side effect of the PG Bouncer that we're taking advantage is you can, on the fly, change the backend database that it points to without having to restart applications or databases or anything like that. So we can kind of, if we have a failure, we can use PG Bouncer to change its backend, and it's a fairly seamless transition to the application, where before changing the database backend, you kind of have to restart the application. And that is not so seamless. Finally, console. This is our first use in Omnibus of console. I know the production team has used it somewhat themselves to some success. So when we're looking at this part of HA, we did have to have a big discussion of the appropriate product to use. So there was we did compare it to etcd a lot. There's a lot of back and forth on that. They were both very close. We ended up with Console. If you want more details on what the discussion was there is a link to that discussion there in the presentation as well. It was not a simple decision, but we ended up with Console, and it has been pretty good to work with so far, so I don't think it was the wrong one. It provides service discovery, so you can, it keeps track of different services and who belongs to the service. So other tools can say, who should I talk to for this service, and Console should have the right answer for that. It also provides a key value store, just a simple service where you can write data to, central location, and other people can query that data. It sounds very simple, but it has a lot of other uses. So we use it a lot for the HA aspect, and I'm sure, for Postgres HA, I'm sure we'll find other uses for it as well. This is only the first feature we're really taking advantage of it. It does run as a server agent, so we have a central cluster of Console nodes that are running as servers. They do a sort of HA themselves and kind of maintain that everything, and then every node that needs to kind of interact with Console has to run an agent as well. So you're not directly, the services aren't querying Console servers directly. They query their local agent, and their local agent worries about connecting to the upstream server, getting the information they need, as well as the agents will then kind of perform the different tasks, like running for service watchers and everything like that. So the database nodes, they report their health status to Console. They have a script that they run that checks if a node is a master or not. If the node is a master, that they report a healthy status to Console, and then Console will then tell PG bouncers that when somebody asks who's the Postgres service, then Console will return this service. If a service is a standby node, it'll report critical, so Console will not offer that up. That is the one downside of Console, is it does not have a concept of a single master service, really. So a service, you're either healthy and it will offer you up as a node for a service, or you're not healthy and it won't offer you up. So that's a minor glitch, so it was easily worked around. We're not too concerned about it, but for just for pedantic purposes, it would have been nice to do that, but again, not a big deal. And PG Bouncer will then queries on startup and queries Console, says who's the database node. Console will return the master, and on a failover, we use what's called a watch. So PG Bouncer node does a watch on the Postgres service. So anytime there's a change to that, PG Bouncer is going to pick that up. It will update its configuration and reload, and then point to the new master backend. I did put in a point about DNS discovery. This is kind of a cool feature of Console in that you can use it as a DNS server, and then you query a particular DNS name, and it will return the appropriate master. So for like the Postgres, if you query PostgreSQL.services.console to the DNS port on the Console server, it will return the current master for the Postgres node. This is neat, but it doesn't really fall within our goal of keeping everything within Omnibus, so we couldn't take advantage of it ourselves, but it is not something we've explicitly disabled. So if users want to do that, they can. And then this PG Bouncer will just that has its own built-in TTL setting for DNS. So you can say, here's the DNS server to query. And then whenever that changes, whenever Console sees a new one, as soon as the TTL expires, PG Bouncer will do a new DNS query, pick up the new master, and automatically do everything itself. You don't need to use anything extra special there. So again, it is pretty neat, but not something we can really advocate for Omnibus. So I'll now do a quick failover demo. First we'll go over kind of what you can expect to see, and then I'll have to jump out to show you a video of the failover, and then move on from there. So the first is what exactly is anatomy of a failure. The first step is the current master fails. This can be for really any reason. You really can't predict it, basically. It's always going to fail in new and exciting ways, so won't get too far in that. But what's going to happen is the other nodes in the cluster are going to see that they can no longer talk to the master. There's a timeout. By default, it's a minute, but it's totally configurable. They'll all kind of sit there and panic, waiting for the master to come back when that timeout. After that timeout hits, they'll start holding an election. They're going to start the election process. Basically, the first thing they do is they can make sure they can all talk to each other, and then after they're done talking to each other, they can confirm that. They then look for the latest LSN to basically who has the most up-to-date copy of the data. And if they're all equal, then it kind of goes for it's basically there's a priority field in there, and then there's kind of different levels, but basically whoever has the latest copy of the data is a viable candidate. They'll all kind of agree. There's an algorithm they use to select who's going to be the master. And once they all agree, MGRD will promote that node to become the master and then tell the remaining nodes in the cluster, follow this new guy. So once they're all promoted and following, console health check is going, the new master's console health check status is going to change from critical to healthy. So that will update in the central console service. So the watch service on PG Bouncer is going to see a change to that service. It is then going to update the PG Bouncer's configuration template and do a reload, and that'll have it pick up the new database backend, and within seconds, then the application will just start, PG Bouncer will start shifting traffic to the new master, and the application should just pick that up seamlessly. So I'll start off, this is what a healthy cluster looks like. You can see in the upper left-hand pane, this is the console cluster, all the different members. We've got 3 console servers, 3 database servers, and a PG Bouncer server. Bottom left pane is the database. The database is in PG Bouncer, where it's currently connecting to. So you can see that the host matches the IP address of IBOM DBA in the console cluster, so that's the current master service. Upper right-hand corner is the health status of the PostgreSQL service in console. I did filter it to just show the passing server. If you were to not query for passing equals true, it will show you the other 2 servers as being critical. And in the bottom right-hand corner is the cluster show command from repmgr. This is just repmgr's viewpoint of the cluster. So we see that we have DBA is the current master. We have DBB and DBC as standbys, and they're both upstream DBA. It says upstream because you can also do cascading setup with repmgr. It's not something we've documented or recommended, but if you wanted to have standbys follow other standbys, you can do sort of a tree. So there are reasons you might want to do that, but we're not currently recommending it.
What is the election process from Rep Manager? How do they talk to each other? Do they have a TCP socket, or are they using some other?
They use the standard way of just basically like the same IP SQL uses to talk to remote database nodes. They make sure they can open a standard Postgres-like network connection.
Sure, but then when they decide that a node is down, there's an election process, right? Is that happen? You said that happened on Rep MGR, right? They have to communicate amongst each other? The
only communication amongst each other that they do is to make sure they can talk to each other. And then from there, they have an algorithm that they follow that should lead them all to make the same decision as to who the master is.
So there's an election, right? They have an election that says, my guy's down, we've got to nominate somebody else.
So they agree to hold an election, and then after that, they kind of follow the same steps to decide who's the best candidate for a master.
Right. So they have to talk to each other. So what is that message bus? Is it a port they all talk to? Is it console? Like what exactly is that?
It's a Postgres connection. It's a standard connection on port 5432.
Okay. I'm not sure I completely understand, but I'll look into it.
Any other questions at this point? All right, I'll switch over to I have a video. Google was kind of distorting the video when I was embedding it, so I've kept it separate. I will do my best to kind of play and pause so I can explain what's going on. So to start, on the left-hand side, this is the PG Bouncer log. On the right-hand side at the top is the failover log for the service that's watching the command that's called whenever that PG bouncer the console watcher notices a change in the PostgreSQL service. Below that, the cluster show, just the current state of the cluster, and then the bottom two windows there are the rep mgrd log on both of the standby nodes. So I'll play for a little bit here. I'm going to stop Postgres on the master to cause a failover, and you're initially going to see that immediately the other nodes start to notice that something is wrong. I set the timeout to 10 seconds for the demonstration. This might be a little quick for production usage, and you'll immediately see on the top that the console loses the master, and the failover will do nothing because it doesn't find a new master yet. And let's see. So now we see the timeouts happened. In the bottom one, you can see that connected to server is promoting standby. So the bottom server is getting promoted to master. Standby promote successful. We'll go a little bit longer. You should see the next one. And then you see above that, you'll see that the other standby node sees the new master and is now pointing to that node. And you'll see in the top window that it's found a new master and it's running the notify command to update PG bouncer. So that's pretty quick. I cut the video a little soon, so we actually don't see in the PG bouncer log that it's getting the new server, but I mean, trust me. Sorry, Zoom crashed on me. Give me just a moment to get back up and running. All right, can everybody see my screen again?
Yep.
So we're in the recovered cluster. Same view. Upper left-hand side is the console members. Nothing's changed there. Bottom left-hand, you should see that the host has changed for PG bouncer. It's now pointing to the new server. Console in the upper right-hand corner is seeing a different master as well. And in the lower right-hand corner, you can see that we have C is now the master, B is still standby, is following C, and we have A is now failed. So we shouldn't be seeing any traffic going there. That is something we're working on in the future. We're looking at having, as soon as a node fails, having it just being evicted immediately from the cluster, so you may not see that view going in the future. And that is something we're going to be doing to kind of prevent a split brain situation where if it comes back and if it still thinks it's the master, it's going to kind of accepting rights, and that is problematic. So this was tough. We've been working on this for a while. So we ran into a few challenges. The first thing, pacemaker core sync is tried and true. We were using it beforehand. I've used it in previous things. It's been around for a while. It's stable. It's also complicated to build and package. I had a proof of concept done where it added, I think, 150 megabytes to the uncompressed omnibus install, as well as it was about 10 dependencies it needed in order to be included in the omnibus. So that was a little bit too complicated for what we're doing. The second thing is we need to keep this as generic as possible. We can't assume that users and customers have specific infrastructure in place or things they can use. We needed to kind of keep it all within GitLab Omnibus itself. And that sometimes was difficult, but it keeps it flexible, keeps it usable. So we stuck to that. Split brain prevention is a concern with any HA solution. So we ran into the issue of, so the reason console is in there in the first place is because you can't assume that one node is going to run a command on another node and then that's going to work and everything's going to be hunky-dory. You kind of have to, every node has to be able to figure out what it's supposed to be doing on its own and know who to talk to and who to ignore. And so that is complicated. So that was something we were still working on, but I think we've addressed most of our major concerns on that one. And the last challenge is this is not boring. HA is very complicated. I know boring solutions are one of our goals, and we did the best we could to kind of stay as boring as possible with this, but there are many moving pieces, and we had to make some decisions to not stay boring where it was necessary. So here, there's more information. We have a documentation page if you'd like to follow up and spin up your own HA cluster to give this a test. We totally recommend that. We welcome all feedback and questions or anything you might have on that. There's the links to all the different components we've included in order to get this working. And the last link is another link to Yorick's database blog post about scaling database. And that should be about it for me. I will stop sharing so I can see the chat and answer any questions.
Can you think a little bit about like how a customer might go about installing this, like a typical deployment?
Sorry, one moment. Sorry, what was the question?
Just asking if you could talk a little bit about how a customer would, what a typical deployment might look like compared to non-HA Postgres.
I mean, well, I guess the first aspect is you're going to need more nodes than you typically have. So you're going to have to kind of plan out your install. It's going to be a little bit more complicated. So you're going to have, with just Postgres and non-HA Postgres, you need one node. With this, our recommended minimum is so 3 console, 2 database, although we might want to update that to 3, and 1 PG bouncer node. The PG bouncer node can run on the application node, so you can kind of consolidate there. So you're looking at basically, instead of 1 node, a minimum of 5 nodes. So that adds some complication to that.
Console has to run on its own server?
Yes, the console nodes should be their own server.
When you're speaking generally about HA, usually you aim for separate nodes to make sure that one failed node doesn't take out another unrelated service. So yes, we kind of do recommend having a separate node for this.
Any other questions? I guess if there are no more questions, feel free to take a look at everything. Please go through the documentation. Reach out to us in the build channel with any questions or concerns you want to have, or just reach out to me directly as well. Thanks very much for your time, and have a great evening or day, as the case may be.
Thanks, Ian. Appreciate it.